Hi, everybody. Let's get into it. So last time we talked about hybrid methods, like hybrid trajectory optimization methods for dealing with contact, and specifically kind of focused on legged locomotion stuff, and did a hopper at the end of class. So there's lots more to that story, and we'll talk a little bit more about that stuff today. Those things are useful for more things than just locomotion, obviously, even more things than just contact and robots. Also super useful in manipulation, obviously, but lots of other applications for things like that. So it's good to know about. Today, we're going to kind of finish up the story from last time, and I'm just going to give a quick kind of overview about what it looks like to do that stuff when you have to worry about friction, which shows up in lots of robotics applications, manipulation, walking, obviously, but also some other things. So we'll talk about that briefly because we kind of glossed over that last time. And then we're going to switch gears a bit and talk about we'll give it like a big picture, talk about what to do in general in this kind of with these kind of tools that we've been talking about when you have model error or model uncertainty, how to deal with bad models. And then specifically, we're going to talk about an algorithm called iterative learning control. That is one sort of pretty like surprisingly effective algorithm that works really well. It's been around for a long time. It's not super new, but is super, super effective in dealing with kind of like if you have a reasonable nominal model, but there's some model mismatch, model error. This is basically a technique for mopping up the errors in your model using rollouts or trials or whatever on the real system. So let's you kind of do some nominal stuff like we've talked about, then go do a handful, like usually order 5 or 10 rollouts on the real system and just dial everything in perfectly, basically. Okay, so any questions about anything at all, like anything we've talked about, any of this stuff, what we're going to talk about? Everyone feeling good? Okay, so let's get into it. So the friction story. This is kind of a very robotics-y topic, but just to kind of give you a little bit more flavor for what's going on here, because if you go do any of this stuff on legged robots or you're going to see this stuff, so kind of to give you a taste. Before, in the stuff we did yesterday or last week, in this hybrid setup, we basically assumed, like with the hopper, we assumed sticking contact, right? So we assumed as soon as the foot touched the ground, that was it. And it was basically pinned to the floor. This is basically like, you can think of this like an infinite friction, no slip kind of assumption, right? That's not necessarily a realistic assumption, as you can imagine, right? Like if you push too hard in the tangential direction with your foot, eventually you're going to break stacked friction. It's going to slip, right? And this can obviously lead to face planting if you're not careful about this. So there's a few ways of dealing with this. And I should say also, like we talked a lot about impacts last time, and that's sort of obvious to think about, slamming into the ground, velocity, discontinuity, non-smooth. Turns out this friction step is also non-smooth. So contact's just bad all around. And in particular, in the friction case, the stick slip transition is non-smooth, right? It's basically like if I'm pushing on a brick, push, 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 at a certain point, it's all of a sudden breaks free and starts sliding, right? And if I imagine if it's sliding, all of a sudden it just stops, right? And so how do we get at that? It's very similar in a sense to the impact story. Non-smooth, gradients are not nice, blah, blah, blah. So we have to play similar games to reason about friction as with impacts. And there's some standard tricks. So we'll talk about a few of those tricks right now. So the first kind of thing to do is just talk about how we model this standard Coulomb friction stuff. And the standard thing is like the most basic Coulomb friction model is something called the friction cone. And we can write this down as a set of constraints. So in the problems we did last time, like a very simple thing to do is to say, okay, I don't have infinite friction. I'm still going to do my hybrid thing. But now what I'm going to do is when I'm in contact, I'm going to add additional constraints that say the friction force, the tangential force has to be inside the friction cone, cannot violate Coulomb friction. And as long as I put a pretty conservative inner approximation there, like a conservatively small coefficient of friction, this will basically generate trajectories that won't slip. So that's like the first thing to do. And that's what most of these methods actually do. Let's write that down. So for each contact point, you would do something like this. So we talked about this, I think, briefly before. So if the friction, the tangential part of your contact force, the friction vector, we'll call that B. So that's a 2D vector. The 2 norm of that thing has to be less than or equal to friction coefficient mu times normal force n. So this guy is friction force, and this is a 2D vector. And then this one is the friction coefficient. So positive scalar, and then this one is the normal force. And we've kind of done this before, but basically what this is doing is what that math says is if you imagine your contact point on the ground and the normal force in the vertical direction and the friction force in the tangential direction, those things have to lie inside a cone. So if this is like n is the height of the cone, then b is sort of a vector that has to lie inside the cone. And so when we talk about stick-slip behavior, the way this is working is if I'm sticking, it means the friction vector b is in the interior of the cone. It means that I have enough friction to keep it still. And then basically what happens if I imagine pushing on my brick or whatever, eventually, so the friction force is going to counteract my pushing force, right? Up until I get to the boundary of the friction cone. And when I hit the boundary of the cone, there's no more friction to be had. So at that point, when I hit the boundary of the cone, if I keep pushing the brick harder, there's not enough friction anymore because I'm at the boundary, and that's when I start slipping. So essentially, interior of the cone corresponds to sticking friction. Boundary of the cone corresponds to sliding or slip behavior. And that's kind of how you get at the non-smooth stuff. So in principle, we could write this constraint down. It's a conic constraint, which is convex. We could write this down in our MPC controller or whatever and just do it as is. But for kind of historical reasons and computation reasons, that's not what most people do in practice. Most people do QP-based MPC, as we've discussed many times. So there's a standard trick that I'll tell you about right now that effectively linearizes this friction cone so that you can stuff it into a QP instead of having to solve a second order cone program, which would be the kind of nominal thing with that cone. So here's what that looks like. So I'll write it down and we'll talk about it a little bit. Basically, okay, so the standard move is to change that conic constraint or 2 norm flavored constraint on B to one that looks like this. We introduce this new vector D that is less than or equal to mu n. E here is a vector of, so let me write this down. So D is going to be a 4D vector where B was a 2D vector. And then E here is a vector of 1s. And we have this guy, and then we introduce a new constraint, d greater than or equal to 0. And we say b, the original friction vector, is equal to the following thing, where these guys are 2 by 2 identity matrices. Okay, so can anyone see what this is doing or tell me what this is doing? So basically, I double parameterized b in this d vector, right? And what I did was split it into the first 2 elements of d correspond to the positive part of b, and the last 2 components of d correspond to the negative part. And I set it up such that all of d has to be positive. And then if I want to reconstruct b, I basically just do the first 2 elements minus the second 2 elements. So I can represent any b here, but I've done it in this way such that it's like twice as many elements, but they all have to be positive. So does that make sense, everybody? So in that case, what is E transpose D doing? Can anyone tell me that? It's so E transpose D is just summing all the elements of D, right? So it's got to be positive, right? Because those are all positive. In terms of B, the original friction vector, what is that thing? What norm? Yeah, exactly. So it's the sum of the absolute values, which is the L1 norm. So what I've done by doing this is gone from the original setup with the friction cone was a 2 norm. This is a 1 norm. It just so happens that like, this is, by the way, kind of a standard trick. You can write down 1 norms as LPs, as linear programs, by basically like introducing slack variables and like linear constraints like this. You can make it sort of into basically a set of linear inequalities can get you an L1 norm, which is kind of cool. So the reason we do this is really such that it can be written down as a linear constraint. So this thing, let's just write this down real quick, equals 1 norm of B. So what this is doing geometrically now is I went from my nice round cone, the original friction cone, to this thing is basically giving me a friction pyramid. It's an inner approximation of the original cone that's sort of like a 4-sided pyramid. So it looks like this now. So like something like vaguely like this. My drawing skills are subpar, so I apologize for that, but you get the idea. And then this would be like, typically we set this up so it's an inner approximation of the original cone. So it's a more conservative approximation, right? So if you satisfy this set of constraints, you're basically like being more conservative than the actual friction cone. Yeah.
Yeah, I'm kind of lost as to what you're doing with D again.
Okay, so the gist is what I want to do is I want to linearize that round cone thing, right? So the nonlinear thing in there is the 2 norm. I want to linearize this whole thing so it looks like so I can put it in a QP with linear constraints. So what I did was, it's this whole setup, right, with all these constraints. So I have this D vector, which is twice as big as the original B. And what I basically did was say, D has to be positive, like all the elements of D has to be positive. And I want to use it to represent the same friction vector, right? So the last line there shows you basically what I did was set it up so all the elements of D are positive. And then what I do is if the positive components of B will go in the first 2 elements, the negative components of B will go in the last 2 elements. And then I can just do first 2 minus the second 2 will reconstruct the original B, right? So now the cool thing about that is everything in D is positive. So if I just sum the elements of D, that's giving me some of the absolute values of the original B, which is the 1 norm. Does that make sense?
Yeah.
Cool. So it's basically a hack. It's like a clever trick for writing down a 1 norm without actually writing down the 1 norm explicitly, right? Because the 1 norm is this pointy, annoying thing with bad gradients. This is just a bunch of linear constraints that gives me the 1 norm of B. So what that whole thing is really just another way of writing 1 norm of B less than or equal to mu n. But now I've done it with like a whole bunch of linear constraints. So it's very clean and it can get stuffed into a QP solver in like kind of a standard way. And we do this because there's lots of nice QP solvers and it's very fast and very robust. And we're kind of very used to using QPs for MPC. So if I can write this thing as a set of linear constraints and stuff it in a QP, it's like a win, right? And so people have been doing this for a long time. Like the original version of the friction cone is convex, right? So in principle, you could just stick with that and not do this, but then you have to use, you can't use a QP solver. You'd have to use a second order cone solver. Those are kind of newer and less sort of, there's less sort of work on using those for MPC. I mean, recently there is, like last 5-10 years, but like it's a newer thing. They're not as fast and robust, and like there's fewer options. So there's pretty much only one like decent open source SOCP solver. It's called ECOS. Whereas there's a bajillion QP solvers, and everyone's very used to using QPs for control. Been doing that for like decades, right? So this is like a pretty standard trick so that you can set this thing up as a QP, basically. Okay, yeah.
So in cell level time, they produce the how that transforms into like a cone. Sorry, to like a this upside down pyramid.
So, I mean, that's basically, I'm just telling you that's what that map is. It's that's the picture for this. It's like the original thing was a pyramid, or it was a cone, and this is like this pyramid thing. I mean, basically what you can think of it as is that's what the one norm looks like. So one norm is like sum of absolute. If you draw like the unit ball for a one norm, if you imagine like if I say one norm equals 1 in the plane, it looks like this. Does that make sense? It's sort of this pyramid shape.
Yeah.
It's kind of weird to think about. So,
Oh,
oh yeah, if I draw like, you know, absolute value of X sort of thing, it's like that V shape. This is basically the level set of that thing in the plane in 2D is like a diamond shape. So a 2 norm's a circle, right? And this cone is basically just sort of like extruding that 2 norm vertically. So for a 1 norm, if you imagine the level curve of 1 norm is this diamond, like level curve of an infinity norm is a box. So for any norm, you can draw this kind of level curve shape, and then this is basically just extruding it up. If you like to think about it that way. I don't know. Does that help at all?
Yeah.
Okay, cool. Okay, anybody else questions on this? Yeah.
What was the name of the solver you said?
ECOS, ECOS. It's the one, if we used it, if we did an SOCP in class, we would have used that. It's in Julia. You can do package add ECOS. So if you want to do any second order cone stuff, MPC on anything, that's basically the one to use. So if you want to do rocket soft landing or any of this stuff, it's not as fast as OSQP. But in principle, you could make an SOCP solver that fast. Yeah.
A very small doubt, like B vector is like right now only 2-dimensional, but so is that why we can only have like a 4-sided pyramid? Like,
oh yeah, no, this is a good question. You can in principle make that approximation as tight as you want. So you can make a 8-sided pyramid, 16.
That work in the identity matrices, because after that everything will be 0, right? After the second column.
Yeah, so okay, so this is a bit weird. This is called a convex combination. So like you basically, I guess you can do it, I promise. You can make it as many sides as you want, and you can look this up. There's like papers on how to do this. Yeah, so that's a good point. So the reason typically we don't do that and we stop at 4 sides is that the more sort of the better you want to make that approximation, the more decision variables you have to add and the more constraints. So it makes the problem bigger. And practically speaking, like this is good enough for most robotics things. Like what we're trying to do here is just ensure that the controller is not going to exert so much torque that it slips. We're trying to be a bit conservative here anyway. And usually when you do this, you'd use a mu that's like conservatively small to make sure you really don't avoid slipping. So this is giving you an even more conservative inner approximation. And that's usually, this is kind of like a safety constraint type thing. So you want to be safe. If you really wanted to push the performance limits up to the edge, then you'd maybe want to do something like you're saying, or just do the original cone. Right. So that's the other thing. Like the other thing is that like at a certain point, if you're making the QP bigger, the performance win is not there anymore. And you might as well just use the full original round cone, right? So in certain areas, you do care a lot. So in one example where people do like want to push this right to the edge and get as much as they can is in driving. There's a lot of work on like racing, like aggressive fast driving. And there, the game is all about going as fast as you can and as hard as you can in the corners. And the optimal thing is to push right up to the edge of this friction cone, right? So there, you really want to know what the mu is and be very exact with this and really use the full thing. So people who do racing use the original full cone and not the approximation. But a lot of legged robots people will use the approximate version. Okay, there's a lot of friction cone conversation. Is everyone good now? Okay, excellent. Okay, so I will now write down exactly what I just said in words several times. So So yeah, friction pyramid, easy to do with QP. And this is the sort of thing that's standard in like quadruped controllers now. To keep your foot from slipping. What else? Yeah, generally in a hybrid method, you're doing this to avoid it slipping. So that's the game here. We're trying to be safe, not slip. If you want to model stick slip behavior and like take advantage of it explicitly, in a hybrid setup, you need to add more modes for that explicitly. So you'd have to add slip modes and it gets really nasty and people generally don't do that. There's sort of other ways to get at that, but it's very messy in general. What else? Yeah, so friction is hard to model. Just as a final sort of, this whole thing is Coulomb friction, which is like a very kind of first order model of what real friction is. So all of this is still approximate, right? And yeah, typically in real applications where you don't want to slip, use a conservatively small mu. Okay. I think that is all the. No, chat. I'll try to keep it on. That's better. All right, cool. Okay, so that I think that's it for that. That's pretty much the end of the discussion on like hybrid contact flavored stuff. That kind of continuing from last time. Any final thoughts, questions on this stuff? Pretty good. Yeah. Sorry, say that again. Yeah, so like anisotropic and anisotropy in the friction. Usually that's not a thing. That's a very weird thing to happen. So if you wanted to do that, then like mu would become a matrix, right? Not a scalar anymore. And this is yeah, do you have a specific application in mind where this happens?
Can we make any use of this in vehicles or?
Yeah, no, this is very standard in like car models and things like this. Yeah, so I guess it's totally possible. I've not seen people really do it before, but you could, right? Like the next sort of version of this, if you wanted to model that, would be replace this scalar mu with a matrix mu that captures different friction in different directions. And that would result in a friction sort of in like a elliptical cone, right? So yeah.
Like in applications we're using in L1 where there are more dimensions, like it's known for like inducing more sparsity in the solution. Since D is only 2-dimensional, does this not a more sparse D would mean like either moving more in X and more?
So it does this, which is a bug. So this is an approximate. So where that shows up here, where that manifests itself in this context is if you're in normal friction land, right, you're going to slide in whatever direction you're pushed. Here, what will happen if I shove a brick, say, because of that sparsity inducing L1, what that's saying here is basically this thing will peg itself in one of the corners of that pyramid, right? Which is physically wrong.
Change your reference direction.
You could imagine like trying to adapt that, but practically speaking, like at the end of the day, like usually when people are using this, you don't want to slip, right? You're using it as a conservative inner approximation thing to say, stay strictly in the interior and don't ever get to the edge. But yeah, if you just naively do this in a simulation to model Coulomb friction, and say like my x-axis is here and I push it like this, the friction vector will peg into that corner, and then your block will like do weird drift sideways kind of stuff that's totally unphysical. So yeah, it's a good point. That's sort of part of the it's not a great approximation story. Yeah. Okay. There are lots of other fun like lasso style L1 tricks you can use in control in general. This is a place where you don't want to use it, but it's sort of got some weird artifacts as a result. All right, so changing gears. We are now going to talk about like what happens when your model is bad. And this is a big topic. So I want to sort of give a sort of high level, I don't know, set of ideas here that like you might encounter, you might hear about, things to check out. Definitely not the full story, but like at a high level, the way I think about it, I guess. First off, we're doing model-based control in here for the most part, and models are always approximations as an engineer, right? So there's always limits to what these things can do, and like you should always be skeptical and always sort of never trust these things all the way. That's sort of the first philosophical point. So then building on that, right? Simpler models are often preferred in control, even if they're less accurate. So like it's often the case, like in principle, we could write down super accurate physics models that have tons of stuff in them that model everything really well, get tons of accuracy, but practically like those more complicated, more nonlinear models are really unwieldy and hard to deal with, right? So usually in control, like if we can get away with it, we use linear models because they're really easy to work with. We know what to do with them. Even if they're inaccurate, like we still use them a lot. So that's sort of the next thing to say. So yeah, basically in general in control, you want to use the simplest model you can get away with. And then like a lot of times we can get away with that because feedback sort of inherently like corrects for some of these errors, right? So like, and a good example of this is we talked about before. If you're trying to do reference tracking or stabilize a fixed point, like you linearize about that point, the model error gets bigger the farther out you are from the fixed point that you linearize about, but the controller is pushing you back. So it's kind of always keeping you in a region where the model's good. And like in a lot of cases, these feedback policies can mop up a lot of the error. Like you can think about the error in a lot of cases as a disturbance, right? Whatever the delta is between your simple model and the real system, like that's you could imagine that as some force on the right-hand side of your model. That's like a disturbance, and the controller is going to try to compensate for that, right? So you can get away with a lot of sort of slop in your model, but sometimes that's not good enough. So like, for example, very tight constraints, like critical safety stuff. That you can't violate, or really sort of tough performance requirements where you're really pushing the limits of your hardware. Stuff like that. Okay, so basically, if the model you have or the model you can easily write down is just not good enough, here's some options to think about. So the first one is maybe the most classic and most obvious, is to do parameter estimation, classical system identification kind of stuff, also known as gray box models. So this would be sort of like see, called system ID. And the idea here is I have some model from physics or whatever that has some parameters in it, like masses, lengths of things, inertias, whatever, that I don't know super well. And I'm going to go collect some data on the real system, do some experiments, whatever, and just go and fit the parameters of my model. Okay, so things about this. First one is it's extremely data efficient. So you can fit this with like really minimal experiments, right? So very sample efficient. It generalizes in that like now I have a model for my system, so I can do whatever I want with it. And I can use this in all kinds of other controllers in different parts of the state space, all that kind of good stuff. So that's nice. But the downside is that it assumes fixed model structure. So examples of like, this would be say, so the quad rotor stuff we talked about, right? We wrote down this really simple rigid body quad rotor model. So I could take that model, go fly the quad rotor around and fit like the mass, inertia, you know, the lengths from the CG to the propellers, like all these parameters in that model. But no matter what I do, I'm never going to capture the aerodynamic effects like lift and drag and weird propeller flapping stuff, like all the weird aero effects. They're just not in that model at all, right? So there's no way I can possibly capture those no matter how hard I try with something like this. So there's inherent limitations to this approach, right? So sort of assumes this model structure. And you're just never going to have, you're never going to be able to capture stuff that wasn't in that model to begin with. Okay, so then building on that, like another idea is to do what's called black box system ID or modeling. And this would be kind of learning a model from scratch using a generic function approximator for like f of xu, say. So like fit a generic function approximator to the full dynamics, or maybe a residual function on your nominal model. This would be called, classically, it's called black box system ID. Okay, so this, and I should say too, there's lots of in between, right? You can like do some mixture of these where you use a parametric model and then add a, you know, sort of neural net thing to learn a residual or learn some part of that or something. So there's ways to blend these together. But on this side, sort of prose doesn't assume a model structure. It's super generic, right? So in principle, this can learn anything there is in the dynamics. And similarly, it also generalizes in the sense that like once you've got the model, you can do whatever you want with it. You can do different tasks with it. The major downside of this is it's not sample efficient. It requires a ton of data to fit, like in general, this very sort of very expressive function, right? With a lot of free parameters. Okay, so that's first two options. And I would say, generally speaking, these two fall in the category of trying to improve your model, right? So there's sort of a couple of other options that we'll talk about next, which fall into the general category of, so let's maybe. Okay, so those methods have the advantage of basically generalizing, right? So the other options are to forget about the model and just try to improve the control policy. And there's a few options there. So continuing with like the number 2 theme, stuff that I'm sure everyone's heard about, you can just go straight up learn a control policy. So this would be kind of the standard domain of reinforcement learning. So like optimize a function approximator for your feedback policy. So like, you know, policy gradient and all the fancier versions of this. So good things about this, number one is it makes very few assumptions on the system, on the model, et cetera. So this can be very general. Downsides, big one is it doesn't generalize. So like basically when you do this, what you get out is very specific to a particular system and a particular task, right? And then like if you want to do something else, that's very hard to do. And then the other one is it's not sample efficient. And here this corresponds to like rollouts or simulation runs or physical runs on the real hardware, right? So cool. Okay. So then there's sort of this other thing in here that is what we're actually going to talk about today, which is sort of to improve a trajectory. So given like a nominal model and some optimal control stuff and like a trajectory that we generate out of doing trajectory optimization, say, we can go take that thing and do some iterative improvement on it using real data on a real system, real rollouts. And that's kind of this ILC idea. And so how that kind of works is assume we have a reference trajectory computed with a nominal model that could be inaccurate. Then you want to basically improve that with data from the real system. Okay, so kind of pros here, makes few assumptions about the model or anything else. So pretty general. Possible downsides, it assumes you have a decent model. So it doesn't have to be super good, it can be quite approximate, but you need a model that captures like some of the dynamics in a reasonable way. So not model free. Similarly to the like learn a policy stuff, it does not generalize. It's like one task, one system kind of stuff. And then the major difference between this stuff and like classic policy gradient type stuff is that this stuff is really sample efficient. So you can like you can kind of like nail the tasks typically with like order 5 to 10 rollouts. So it's very practical to do like sim to real transfer type stuff with this. In fact, you can also like actually learn from scratch with this stuff on hardware. It's efficient enough to really do that. Okay, so this other category of stuff here is sort of improve the policy kind of stuff, right? So kind of don't try to make the model better, just take what you've got and then like try to just make the controller better. Okay, questions about this? Like high level, I don't know how I try to categorize these things. Yeah.
So like when you say generalizes, like any of these where you're collecting data, you're just fitting your model to that data, right?
Yeah.
So like it only generalizes within the space of
Right, it's interpolation. You don't want to extrapolate, you want to interpolate, right? So what I mean there though on the data-driven stuff is that you can, once you've got the model, you can do a different task with it, right? So like these policy things and the ILC things, they're dialing in a controller for a very specific, do this one task. Whereas the model-based things like learning a model, even if you're just, sort of only fitting it with within some region of the state space, I can do any task I want in that region of the state space, right? So I can totally change up the behavior and do something else with it if I want to pretty easily without having to go collect more data, right? Okay, cool. All right, so let's do this ILC thing. Who's heard of this? Has anyone done this before? Not too many people. Okay, kind of cool. Let's do it. So there's a few ways to think about this. You can think about it from several perspectives. So like one way to think about this, if you're a machine learning person, is it's a very like particular specialized version of like a policy gradient method for a very specific policy class, which is the following. So basically, if I have a control policy UK, that's a function of some reference U bar K, reference open loop control. I want to think about it that way, where I've got a controller that looks like some reference control trajectory U bar, and then maybe some feedback policy in here, but I don't really optimize this. This thing is just sitting here. Can be any feedback controller you want, right? Like that's doing reference tracking. So this could be, LQR, MPC, weird neural net thing, anything you want. What we're doing here is specifically looking at this as a function of this like reference trajectory. And we're going to go and optimize that reference input trajectory. So it's like feed forward input to the system. Okay, cool. So that's one way to think about it. Another way to think about it is as an SQP method, like a direct trajectory optimization type method, where we're evaluating the right-hand side vector when we go solve the KKT system on the real system. So we can like compute the whole matrix, using our approximate models, all those Jacobians, Hessians, whatever, they're coming from our nominal model. Yeah.
Could you just clarify again what the letters and subscripts on the left-hand side of the equation?
Oh, sure. Yeah. So that's saying like you are like control inputs, right? Your control like policy looks like some nominal U bar, some nominal feed forward reference, like which could be optimized offline with trajectory optimization, right? Plus optionally some feedback controller that's doing reference tracking. So that K can be any tracking controller you want. right? So like this could easily, so if that's, if that K is a matrix and this is linear feedback, that's like LQR, can be time varying LQR, can be some nonlinear feedback that's doing reference tracking on like the nominal X bar reference track, whatever you want, right? But the key thing is what we're gonna update and optimize here is the U bar, that feed forward control reference trajectory. Does that make sense?
Yeah.
That's like, those are the parameters we're optimizing. We're gonna leave the feedback controller alone. We're not touching that. We're also not touching the model. We're just touching that like U bar in there, which is just a trajectory. Okay, so other way to think about this. Is as sort of an SQP method. Where we get the right-hand side vector. We get the big matrix from the nominal model, but we get the right-hand side vector from a rollout on the real system. You can also think about it as like sort of like a single passive DDP where you do the backward Riccati pass using the nominal model and get all your derivatives that way. And then you do a forward rollout on the real system instead of in the simulation with the nominal model. It's like various flavors of this you could think about doing. Okay, so let's do it. So assume that we have a reference trajectory. X bar, U bar. So the states and the controls that we want to track. Actually, there's various versions of this. This is like one version, a simple version for doing reference tracking. There's other flavors of this. But kind of at the end of the day, what this is roughly doing is doing trajectory optimization with real rollouts in the loop in the optimizer. Okay, so we're going to do min over X and U in the usual way of this cost function. And we're going to assume a quadratic tracking cost. So very LQR flavored. So like X minus X bar, quadratic weights, whatever. And then control cost. Same stuff we're used to. And then terminal cost. Okay. In general, you can have any cost function, right? We're just going to do this for now because it's easy and convenient. So it doesn't have to be this. And then subject to our dynamics, like as usual. Okay, so like we've done before, and we did like direct methods and SQP, we're going to write down a KKT system for this thing. And I'll write this down, and then we'll talk about it a little bit. Okay, so this is going to look a little different than what we've seen before, but same idea. So we've got our, well, let me write it and I'll talk about it. Okay, so this is what we're going to deal with. just defining some stuff. So the Z is going to be all of our states and controls stacked up like we did before. The C function is our dynamics constraints. So like for most of the stuff we do would be something like, f of xk uk minus xk plus 1, sort of the classic direct transcription type of thing. The C matrix, here is the Jacobian of those dynamics constraints, partial C, partial Z. And then the H matrix is our sort of standard Gauss-Newton Hessian. So it's going to be sort of the Q's and R's stacked up in like this block diagonal kind of thing, zeros everywhere else. Okay. Hopefully that's cool. So now some questions. So when I do this typically, so we're basically writing down a Gauss-Newton, thing here, KKD system. So first question is, in the top of this vector here, usually that's the gradient of the Lagrangian, right? When I do this, and so there's some like Lagrange multiplier stuff in there. And here, instead of that, I've written down gradient of just the cost function, right? So that's like a little different than we did before. And the other thing is that usually when I've done this in the past, I've written in the bottom here, when I do the Newton stuff, I usually do delta L, right? Instead of here, I've done the actual L, not a delta update on the L. So what's going on here? Does anyone have any thoughts? Like, why can I do this? Why is this legal? So both of these things are related. Thoughts? Yeah.
Just what's the L?
Sorry, lambda in the bottom. So basically, usually I'd have delta lambda, like Newton update on lambda. Here I put just straight up lambda. And instead of like grad L, like gradient of the Lagrangian in the top right there, I have grad J, just the cost function gradient, right? So does anyone know like what I'm doing there and why that's legal and stuff? Have any thoughts on this? No. Okay, so the Lagrangian, the standard like, optimization Lagrangian, where I have the Lagrange multiplier and the constraint Jacobian, it's linear in the Lagrange multiplier, right? So it turns out when I do this, I've got, it's exact in that Lagrange multiplier term. So C transpose times lambda coming from the top row of that matrix, that's what's in the original Lagrangian. So because it's linear in lambda, I can just write it like this. And then the nominal Lagrange multiplier term that shows up in on the right-hand side vector, I don't need anymore because it's sort of all sitting there. So I'm doing this. This is sort of standard. You can do this in SQP methods in general. We haven't done it this way before for a very specific reason. Which, does anyone have any hints on why maybe I'm doing it this way instead of the way we did it before? Okay, so the reason I'm doing it this way, unlike before, is before we did the delta lambda. The reason is before, when we're doing this in general for nonlinear problems, I need to regularize, right? And it turns out if I want to regularize the Lagrange multipliers, I want to do it the other way with the delta lambda. So I don't know. So you can always do this. But you probably don't want to do this if you want to regularize the Lagrange multipliers. I.e., yeah, we've talked about this before. Okay, I don't know. Fun fact, random thing about nonlinear stuff, nonlinear programs. Okay, so a couple of observations here. So if I have a nominal trajectory and I'm like solving this problem, if I go do a rollout on the actual system, what is C of Z on that right-hand side vector in my KKT system? Thoughts? Sorry? No, so those are the dynamics constraints, right? So let's say, if I go do a rollout and like have this trajectory that's dynamically feasible, that obeys the physics, it has to be 0, right? So, okay, that's first fact. If I do a real rollout, that C of Z thing, that dynamics constraint thing should always be 0. That's assuming like for the true dynamics, right? That might not be true for my approximate, crappy dynamics model, but on the true dynamics, that's going to be the case. So I'm going to go ahead and just set that equal to 0 here, given a real dynamically feasible trajectory from the real system. Does somebody over there have a question? Those are the dynamics constraints. So that's saying like xk plus 1 equals f of xk uk. It's just saying like, okay, so if I simulated this on the real system, that's true by construction, right? Like that's what my Runge-Kutta method's giving me or whatever. So that whole vector is going to be 0. Those are the dynamics errors, right? If I do a direct method normally, I can do an infeasible start, right? Where I give it a bad guess and those dynamics don't have to be satisfied. So that could be non-zero in general for these methods. But here I'm doing a rollout, so that thing's 0 automatically. Okay, so then the other thing is, since we know the cost function, if like we wrote that down, we made it up, we can write down like grad J in that right-hand side vector anytime we want to, right? Like we can just evaluate that. So we can always compute that. So I can just do the rollout, get the trajectory from the rollout, plug it into the cost function, evaluate grad J, right? So now I have a recipe for computing that whole right-hand side vector in the KKT system, the grad J and the C, from any rollout I do, right? So C is always 0 by construction, grad J, I can just plug it in the cost function. Cool. We also know the cost function. We also know the H matrix, the Hessian of the cost, right? That's just stock. We can always evaluate that. It might be constant for a quadratic cost. It might not be. But we can always evaluate it. Okay. So we can also then basically the only thing left that we don't know perfectly from doing a rollout is the C matrix, in those off diagonal blocks, right? And so basically the whole ILC game is we're just going to use the C matrix from the nominal model, but everything else is going to be from the real system. Okay, so you could do that, and like that can work perfectly well. But what we're going to do today, and what is kind of standard practice with this stuff, is to instead, like if you're using this from scratch, if you were to try to do from scratch, trajectory optimization on the real hardware, you'd probably do that, and that can work. Instead, what we're going to do, which is maybe more common, is we're going to do this sort of offline, online, sim to real transfer type of thing, where we're going to say offline, we're going to optimize the trajectory using just the nominal model, using standard trajectory optimization stuff. And what we really want is for the real system to perfectly execute that task, track that trajectory, whatever, right? And so what we're going to do then is, assuming that that offline optimized thing is pretty close to the right answer, and that our nominal model is not too terrible, I'm just going to compute the KKT system offline once, where I linearize it about the reference trajectory that I compute offline. And then assuming that that model's not too bad, when I go run it on the real system, I shouldn't be too far off from the reference. Does that make sense? So therefore, the linearizations from the reference computed offline should be kind of good enough, and things should converge. So this turns out to work pretty well. And that's what we're going to do. Again, you don't have to do that, but it works a lot of the time. All right. All right, so we compute this Jacobian thing once offline. Okay, now all we have to do is basically online, we do a rollout. That gives us a new right-hand side vector. And then we just have to do a single linear system solve with that KKT matrix that we've already evaluated and already pre-factorized in general. So it's really fast and cheap. So we solve this thing for this delta z in that left-hand side vector. I mean, in general, delta z and lambda. We don't care about the lambda. We're just going to take the delta z. We're going to update our u bar. That delta u, and then repeat. On top of that basic setup, you can also easily add things like inequality constraints for torque limits and stuff like this. And instead of just solving this one linear system, we just solve a QP. It's also pretty standard. Okay. So questions about this? Yeah. Oh, you do solve for it. Like you're gonna solve that linear system and get delta z and lambda. It's just that we don't use it for anything. So I'm just trying here to update the u's in the nominal trajectory. So I'm not gonna use the delta x's either. I'm just gonna solve this thing and then pull out the u's from it and use that to update my u's. The rest of it's like baggage that I don't necessarily care about. I don't know if does that make sense? Okay, anybody else? Yeah.
I'm just a little confused. Where are the errors coming from in this system? Like if we design our trajectory using an f of x like function, that was actually not correct.
Correct, yeah.
And then, so how are we doing the rollouts that account for the things?
So the idea here is I have some system. I have some model of the system that's f of xu. but the model's not correct 100%,
So
right?
what do we use to actually do the rollouts that are?
The real system.
Oh,
Yeah, so this
So
is
you're
like,
like
I have
training.
math for this thing
yeah.
that I'm gonna use in the computer to like compute this stuff. Then I'm gonna go take the controls that I get from that, go run it on the real thing in the real world.
And do data.
There's gonna be
logging
some,
stuff.
yeah, exactly, log a bunch of data, there'll be deviations from what I expected. I'm gonna take those deviations and then feed them back into this, do a correction, and then try it again on the real hardware. So this is like a way of basically like polishing your solution on the real system, given the sort of offline math that you did before using the approximate model. So there's a lot of ways of thinking about this. You can think about it from a bunch of different perspectives. You can think about it from like a sort of RL perspective. You can think about it from like a, I don't know, SQP, direct trajectory optimization perspective. You can also think about it from like a, I don't know, almost linear feedback perspective. You can think about these updates as actually being like linear feedback that you're doing like sort of outside the loop on the feed forward use. That's a, I don't know, weird thing. Anybody else have anything on this? Yeah.
So the lowercase cx, the dynamic constraints, is the nominal model minus the like the real x from the last iteration or something.
So no, this like you mean this C vector that I'm defining here? No, so this is like just the standard dynamics constraints that you would have in your trajectory optimization problem, right? Like xk plus 1 equals f of xk uk, right? That's just the model, the nominal model. That whole thing is the nominal model. What I'm saying is like if I did offline trajectory optimization, got this trajectory, this is what I would use, right? What I'm saying now is we're gonna like take that, go run it on the real system. It won't perfectly match, right? And like there'll be deviations. I'm gonna take those errors, I'm gonna stick them back in that right-hand side vector and like resolve this to get a correction. So it's using the real errors, but the nominal crappy gradients basically to get a search direction to improve the errors. Does that make sense? Normally, when I do this in a trajectory optimizer, right, the left-hand side and the right-hand side are all coming from the nominal model, right? So normally, like, I have this model f of x, blah, 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 and I'm using that f of x to compute the right-hand side, right? What I'm saying is, and I'm using it to compute the left-hand side, right? What I'm saying now is, if I do that and I get an answer, cool, I go run it on the real hardware, and now I'm going to replace the right-hand side vector with the real data from the real system, but the left-hand side of that equation stays the same and is computed using the nominal model, the mathematical model that you had before. Does that make sense to everybody? Okay. Any other questions about the basic idea? Yeah.
So this is for like handling purpose model, not for noise and not for environment. Imperfect environment.
So it depends on what you mean by imperfect environment. So this is not doing like, this is not getting rid of like noise. For that, like that's standard feedback controller, right? The feedback controller will kind of like, if you have just like white noise inputs, whatever, that the standard feedback controller can deal with, right? This is like, I was missing a term in my dynamics that like really messes up the results, right? Like if I had some like, so I don't know, there's lots of examples where I'll show you some, but like one way to think about this, let's say you're doing like a really simple example would be like, let's say there's a quad rotor and you're trying to fly a straight line across the room and there's a wind gust in there. Like there's a constant wind blowing, say, this way that you didn't account for in the model. So now if I try to fly straight, you're going to do this and veer off course, right? If you do this ILC thing, it will correct for that and like figure out how to fly in a straight line in spite of the constant wind. Does that make sense?
Yeah, so that also like, for example, if we have imperfect friction model.
Yes, exactly. That's
that will-
exactly the example we're going to do in a second when I,
So it's not necessarily like in an intrinsic thing. It's also
that's right. Yeah, so it can handle like completely weird model errors that are not sort of parametrically accounted for in your nominal model. It can be anything, which is really cool, right? So you can handle like weird friction stuff that's unmodeled, that's hard to model, like this can take care of it. Yeah, which is exactly the example I'm going to do in a minute. Yeah.
So what we're like solving for at the end of this is like a new reference trajectory, like a new X.
Not a new X, just a new U. So what this is saying is like, there's some X that I want the robot to execute. It's not doing that, right? And it's saying, I want to, this, like the tracking, I wrote down a tracking cost, right? It's basically saying, follow the X that I'm telling you to follow. And this is trying to figure out the nominal, like It's trying to figure out the open loop U that should give me that X. Ultimately is what it's doing. It's not changing the X's, it's changing the U's to try to get it to the actual system to execute the X's that you thought it was going to at first. Sort of weird. I don't know. Does that make sense? Yeah.
So just quick to clarify, the part where we actually use the data is in the C of Z matrix, like vector, right?
That C of Z vector is 0 always. So we're not like, yes, but like what's happening is that's the dynamics like errors, right? In a normal SQP method. And I'm saying that's basically if that vector is non-zero, it's telling you that like the dynamics are violated when I solve these things normally. So remember we did like IP opt direct collocation and we did this like infeasible start thing where I drew a cartoon trajectory that didn't obey the physics. And then I solved it and it was able to solve. What's going on there? When I draw the cartoon trajectory, that C is non-zero. The little C of Z is non-zero because I'm violating the dynamics constraints all over the place. And then the solver kind of figures it out, right? So what I'm saying here is I'm going to go run the trajectory on the real hardware and then log the data, whatever, get this trajectory data. Basically, by definition, that rollout is dynamically feasible because I did it on the hardware and it's obeying the physics because I actually did it in the real world. So like by definition, basically that C of Z has to be 0 on the true physics, right? Not necessarily my crappy model. So I'm going to set it to 0. And then I'm going to use the data to evaluate the cost gradient on the right-hand side as well. Yeah. Does that make sense?
I guess I'm still like losing where like in that equation, like you're using like the data from the real world.
Yeah. So grad J for sure.
Right, yeah.
Right. So I'm plugging in the real XU and evaluating the cost gradient. And then also potentially in the KKT matrix, like I could do that. I could use it to evaluate H if it's not a quadratic cost, and I could use it to also evaluate the C's. But I'm saying like basically, usually when you use this, you're pretty close. And so you can just like keep those constant and not update them in a lot of contexts, which is what we're going to do today. And I'll show you that. But yeah, in general, you would use it basically everywhere. And you just evaluate all these things along that nominal trajectory. I'm saying you can get away with some more tricks. Basically, that you can leave the matrix alone. What you're really doing here is updating the right-hand side vector with real data. Yeah.
Assuming low control noise really is one thing updating is those X's in the J rating.
And the U's.
The U's were already, the U's will be whatever you actually, whatever control you actually executed.
Yeah.
Okay, so if there's low control noise, they should be very close to what your U's you did in reference structure, right?
No. That's kind of the whole point of this. This is potentially finding some quite different U's than what your reference was in order to track the X's that your reference trajectory had in it.
Not in the Z. That's we're gonna end up optimizing the Z, right?
Yeah.
But when we go into when we take our data and put it into the gradient of J.
Yeah.
That is the data we collect with both X's and U's
Yes.
in the real system.
Yeah.
Okay.
I think this might be more clear if we just do it.
Yeah,
So we're going to do it, and I'll give you code. And it's on the homework too. But yeah, the gist of it is like stuff on the left comes from the model, like standard trajectory optimization. Right-hand side vector comes from real rollout. And you plug that together and get like a correction thing. You can actually do this like fully on the hardware from scratch if you want to. In which case you'd probably want to evaluate all the stuff on the left, right? And then do rollouts. Like another way to think about this is it's basically like doing DDP or ILQR, where I do the forward rollout part on a real hardware system. And then I do the backward pass Riccati stuff using the nominal models gradients. Does that make sense?
You got to pass first with the nominal model before it passes you.
The ordering actually is ambiguous there, right? But like, so you can imagine like, I could start with some random guess, all zeros maybe, run it on the real hardware, get some trajectory. Now I'm going to do a backward Riccati pass using Jacobians and gradients from the nominal stuff. That's going to get me an update. And I'm going to go, instead of rolling that out in the simulator using the nominal dynamics model, I'm going to roll it on the real hardware and get some trajectory. And then I do backward Riccati using the approximations, right? That's sort of the same thing, actually. It's basically equivalent to what this is. This is just the kind of the more normal way that people do it. Does that make sense? So you're basically doing TradJob with the real hardware in the Newton step somewhere. It's kind of the gist of it. Someone over there have a question? Yeah.
Can you get any like interesting information about your wrong assumptions in post-processing, or is it kind of buried in there?
That's a good question. You probably can. I haven't thought about that too much. Yeah, I don't know. I don't have a good answer for that. Okay. Yeah.
Is there a limit or like some kind of, can we say what kind of errors in the model it can handle?
It's pretty generic. So it's a very black boxy thing. There's not like any real, like basically the assumption here, at least the way I've done it, is that those errors are kind of small-ish in some sense. And we can make that a little more formal. But yeah, basically it's making some assumptions that the true model is not too far away from the nominal one.
The modeling error is big, but you might still be able to like adjust your use.
Yeah. Yeah, I mean, like, it's hard to say anything super formal about this, but basically like, you could imagine like proving convergence of this under some like bounds on the model error. Basically, the key assumption here is that the nominal model is sort of like an okay approximation for the true model, such as getting you in the ballpark, right? And sort of roughly speaking, generating roughly good descent steps on this cost function. Like it's giving you okay gradient information. That's basically what you're assuming here, right? So like if the model is really terrible, it could be pointing you in those gradients could be pointing you in totally the wrong direction and things will be bad for you, right? But like in general, yeah, it's not making any assumptions about like the structure of the errors or where they show up or what kind of they are or that they're smooth or any of that. It's just saying that they're not too big. Okay, anything else? We basically ran out of time now. So I guess we'll finish this next time. Yeah, I think that's probably punt till Thursday at this point because we're there. Happy to talk about other things if you want. You want to see it work? Oh, sure. Yeah. Let's do it. If you want to hang out, I'm always welcome. Like you're always welcome to hang out longer. Let's do it. But yeah, I'll do this next time for sure. So if you guys have to go and take off, that is cool. Okay, so blah, blah, blah. So this is a cart pull. And what we're going to do is first off, I'm going to just solve the nominal problem offline with Altro, our lab solver, in 20 milliseconds, which is pretty awesome. Thank you, Brian. This is a cart pull. Yeah, I'm going to show you that now. Okay, so here's like nominal dynamics with RK4 for just cart pull. I think like the parameters are over here, like I don't know. Yeah, some mass and whatever, but here's what I'm going to do. So this is the nominal dynamics. Here's the true dynamics. What I'm going to do is perturb the masses of the cart and the pole, just stuff I made up that seems like vaguely reasonable. And then I'm going to put some like 5 millimeters of error on the length of the pendulum, like this kind of stuff, right? This is all like parametric error, which is like maybe of a more benign flavor. Then what I'm going to do is also go in and put in nonlinear friction on both of these guys actually. So what this is like, this is approximating like Coulomb friction or stiction kind of stuff, super nonlinear and like not in the original model in any way, right? So you wouldn't get this from a parameter estimation. Exactly. So this is very weird. I could throw anything I want in here in principle, right? But this is just trying to make this like realistic-ish, right? Stuff that you would probably see in practice. So this like Tanch weirdo friction thing. Now we're gonna, I'm gonna generate an LQ. So let's do this first. So this, I'm just gonna roll it out. I'm going to take the reference trajectory from that I computed with Altro, just run it open loop on the hardware. And quite obviously, it's not going to work, right? This is a cart pull doing a swing up, right? So here's like cart pull swing up. And you can see, obviously, like it fails to reach the top equilibrium point, right? Cool. And this is just open loops or whatever. So let's do some more stuff. So what I can do here, right? Like I can add an LQR tracking controller to this to try to track it better. Let's try that. So just LQR. Yeah, so that actually does really well. So you can see just with vanilla LQR, it swings up. Here's the problem. Here's my open loop U. Here's U with the LQR controller. So it's actually violating the torque limits. So if I actually go enforce those torque limits here by just clamping the U's coming out of the LQR controller, it's going to fail. So this is basically, so now you can see if I clip the U's, it just can't succeed because there's no more, room for LQR to do its thing, right? Okay, so now what we're going to do is this ILC thing. So I'm going to get rid of the LQR controller now. And you're going to do this on homework too with some more of this stuff. So, okay, back to what we had before. What I'm going to do now is set up a QP. I'm going to do the ILC thing. So I'm going to have a tracking cost in here with like, what I'm going to do is I don't care about the position tracking very much. So I'm going to put a low cost on that. I care a lot about the theta tracking, right? So I'm putting a relatively big, because I want it to swing up, right? So big cost on theta, small cost on X. I don't really care too much about the R's, the U's, so whatever. So this is what we just talked about, right? So that's quadratic cost. Here's the gradient calculation. Blah, blah, blah. What else? The dynamics constraints are like kind of the standard linear thing that we did before. So this looks a lot like the QP-based MPC thing. And then I'm going to stick in here. The only difference from what we did in the write-up was I'm adding upper and lower bounds on U as constraints to this thing to account for the torque limits. I'm going to go ahead and solve this with OSQP. I'm going to pull out the delta U, and I'm going to go update the trajectory, like in the standard way with the delta U. Cool. So that's one round of ILC.
So can you go back to that? And
Yeah.
explain exactly to where the data from our trajectory comes
Sure, sure. So, okay, so utraj is the real thing that's getting executed, and then like xtraj is the real X. So here's where the real data shows up.
from.
So
That will to
this is in the gradients. So this is the grad J on the right-hand side vector. And then the C on the bottom is zeros.
yeah.
That's it in this case.
So the X is going to grad J, and then the U's get used when you update, or the U trash gets used when you update the.
Yep, that's right. And then what else? Here, and then the utrad shows up in these constraints, right? Because I'm updating it so that U plus delta U, right, has to be within the torque limits. That makes sense?
Yeah. Yes.
Cool. So that's also in the right-hand side. So, yeah.
We sold the AKT system for several times.
Yeah, so here's what we're going to do. So I just solved it once, right? Then I'm going to go do another rollout. So on the real dynamics. So here that is. And you can see like maybe it got a little better, maybe not. I don't know. That didn't look super great, actually. So I'm just going to do this a handful of times. And what we should see is it gets closer and closer to the swing up succeeding. So not so great so far, whatever. We'll do this a handful of times. And what you'll see is within like 5 to 10 trials of this, it's going to like start doing a lot better. So you can see it's starting to get closer to the goal, right? It's always obeying the torque limits. So if I do this a handful more times, it's going to nail it basically. So yeah, now it's basically there. This was like 4 times, maybe like 5 times. So I don't know, we're pretty much there now where it's succeeding in the swing up task. Yeah, so like, there's still a little bit of tracking error, but it's swinging up and hitting the goal state, right? Which is what I mostly weighted in my cost function. And I can keep doing this a handful more times, maybe I'll get marginally better, but yeah, so now it's like almost exactly nailing what you wanted, right? So that was like, I don't know, 6, 7 times of, like you can think about it, 6, 7 rollouts on the real system, right? And then this kind of update on the use. And then this is running open loop also. There's no feedback on this, right? Okay.